Hello, it's a privilege to be here. I'm Stephen from Cambridge, and I'm going to be talking to you about liberating the lurking Smalltalk in Unix. So I better start by telling you what I mean by Smalltalk and Unix. So here's a picture of Unix. So this is Dennis Ritchie and Ken Thompson working away on their PDP-11. And you see they're using a teletype there. So when I say Unix, I'm actually not talking so much about the operating system, but I'm talking about the Unix style of programming, Unix programming experience. So it's very much sort of working at a terminal and using tools like compilers. So for example, we might do something like this. So we run a C compiler and we build a program. It doesn't quite do what we want. So then we edit something and we run the compiler again. We run the program in this cycle, sort of using tools, building a program, running it, then stepping outside, changing it, and then continuing like that. So that's one way of doing programming. And then there's also this Smalltalk thing. This is the sort of iconic picture of Smalltalk when it was released to the public. It featured on Byte magazine in the very early 80s. And this is a very different experience of programming. So you can see this is a picture of a slightly old picture of a Squeak. The Squeak is one Smalltalk implementation. And you might be able to tell that this screenshot is showing you a view onto your program. So it's actually showing you the structure of your program while you're running your program, and you edit your program from inside. So here you can see that we're browsing some bits of code that are in the system, and then we can actually edit them interactively. So it's a very sort of dynamic environment, and we change it from inside. So that's very different from the Unix way of doing things. And when I say Smalltalk, well, nowadays, we have lots of dynamic languages, and maybe they don't all look exactly like Smalltalk, but at least they give us some kind of interactive environment. So the baseline is sort of a read-eval print loop. So when we're talking about Smalltalk, I'm actually going to be quite broad and say Smalltalk is just kind of a touchstone for dynamic languages generally, and the ideal of programming in a dynamic style with a dynamic experience. So just to summarize the contrast between these two, in the Unix world, we have a unit of code, and if it's just on disk, not running, then it's a binary, and if it's running, it's a process. And then we have a VM image of Smalltalk, which is this one thing that we edit it, and then it's always running, and then we can save it to disk and then continue it later. So people say that the first one of those is very sort of static, and I'm not putting too strong a definition on static. It's just sort of what people say. And similarly, Smalltalk is very dynamic because we've seen the differences of the two ways of programming. So one of these differences is that in Unix, we program the thing from the outside, then we run it. So we run the compiler, we've got the source code, we've prepared that separately. Am I still mic'd up, by the way? Okay, good. It sounded a bit funny. We're preparing it from the outside, and then we're continuing to run it. Whereas in Smalltalk, we do everything from the inside, so we're working within the system itself. And similarly, if we want to change stuff, in Smalltalk, we don't have to go back to the outside. We can do everything from the inside. So another contrast with the sort of Unix way of programming, when I say Unix, I could be talking about programming in C or C++, I could also be talking about Fortran or Ada, it doesn't really matter, but it's one of these languages where you compile stuff down and then you run it. So in most of those languages, you're basically aware that you're dealing with bytes in some sense. Whereas in Smalltalk, because everything is kind of an object, and objects have descriptions being the class of the object, and then you have meta classes and so on. This is sort of a descriptive fabric built in to the system. And similarly, if we're worried about the outside world, we want to do I/O, then in the Unix world, we know that that's all happening in bytes, whereas in Smalltalk, it kind of happens by magic inside the virtual machine. So that's the way that we tend to see things. That's the sort of typical view of things. I'm going to do a tiny little demo, which, can you read the terminal on the left, by the way? Sort of, just, sorry? I don't know how to do that, actually. You could move forward. How about that? Okay, so it's a very silly demo, but I do it just to show that there might be more dynamism lurking in the static world than people think there is. So let's try starting a clock, and this is just the normal X11 clock. So it's written in C, and I'm going to run it with a certain geometry to make it look not too small, and then I'm going to move it. So as you can see, it's showing the wrong time. Because I've not changed the time zone on my computer. I came from England, so I'm still on British time. So what can we do to actually dynamically update the time zone of this crusty old clock application without restarting the clock? Any ideas? Yeah, I could do that, but my system time is just set to UTC, so it's really the time zone that I want to change, not the actual. Okay, well, what we can do is use the fact that there is more dynamism lurking in this Unix infrastructure than we thought there was to, what do I want to do? To actually update it when it's running. So hopefully, if I do this, I now have a debugger attached to my clock, which is pretty nice. The clock has stopped temporarily, but it'll catch up. And then we can actually dynamically, we can inject a little bit of code into the process effectively that's going to update the time zone by updating a data structure in the program. So America, let's try Chicago, who knows that one. And then, hey, okay, so we're back to the right time, which is, it's a silly demo, but I just like giving it because it's sort of something people don't expect to work and actually works very nicely. So it's sort of a hint that there might be more dynamism lurking in the static world than we thought there was. So we saw the picture of Ken and Den, the Unix picture with their PDP-11, and that's sort of how, at least how I picture sort of the classic Unix. But actually, you know, in the 1980s, a lot of stuff happened. A lot of stuff got added to the Unix operating system and the sort of user-level software infrastructure that we don't think about so much, but it's actually made quite a big change. So this is a paper from the Unix conference 1984. Tom Killian was talking about how we do debugging in Unix. And he's saying, well, you know, previously we didn't have a way to dynamically bind debuggers to programs. So we just had to have the program expect, you know, it had to make some special system call to say, you can debug me now. So if the program wasn't expecting to be debugged, then you couldn't attach the debugger. So here he said, well, you know, we came up with a new way of doing this that allows us to do dynamic binding, and we tried to make it very uniform with what was already in the design of Unix. So he's actually talking about the proc file system. So the proc file system is a way of making all the processes on your system appear as files, and it's now a standard part of Linux and BSDs. Another thing that happened in the 80s is that this is a paper from, again, the Unix conference a few years later, saying that, well, you know, we can actually build programs as we run them now. So build in the sense of put them together, so link in pieces of code into our program as it's going along, using a revised system link editor, LD, that supports dynamic loading and binding. So sometimes people don't know what a linker is. If you do, then this will be very boring, but I'm just going to do another tiny little demo to show you a linker in action. So I can quit GDB now. And I should probably have a hello world program here. Always have a hello world program. There we go. So normally we'd compile it by doing something like hello.c. And that is actually going to run the linker for us, so we don't see it. But if we just ask the compiler to not run the linker, just compile a single file and not touch any libraries, then it's going to produce us a much smaller file that we can't run yet. And we can look inside that file and see what we've got. Is this what I want? Yeah, okay. So you can see that we've got some instructions here, and the most interesting ones for us are going to be these two. So one of them is loading an address into register EDI, and that's going to be the address of our hello world string. But unfortunately, if you can read the instruction, it's all zeros at the moment. So the compiler didn't actually fix up that instruction. It just says, well, there's going to be some string here, but because I haven't linked in the strings yet, then we've just got to leave a placeholder. And this record here, this our relocation record, is marking where we're going to find the string when we do get it. And similarly, we have a call originally calling printf, but the compiler's been very clever and changed it to puts. Anyway, we've got a call, and that's also the argument to the call is all zeros because we haven't run the linker yet. So if I then run the linker, we'll see that these get filled in. So I'm going to do a static link just to keep things simple. And then if I opt dump hello with a bit of grepping, it should show me. Okay, so now you can see that we've got the same instructions, but they've all linked in. They're actually now pointing at something, which is good. So that's happening every time you compile a program. But, excuse me. But this, the dynamic linker that was added to Unix in the 1980s is saying, well, actually, we don't have to do all that ahead of time. We don't have to do it when we compile a program. We actually link new stuff in as our program is running. So it's sort of a bit more dynamic than we think of Unix. So what's happening here? Well, that's Philip Greenspun, and he's famous, among other things, for coining this aphorism, Greenspun's 10th rule, which says any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of Common Lisp. Okay, so it was Common Lisp, but I think he could have been talking about Smalltalk, so I'm going to pretend that he was talking about Smalltalk. It suits my purposes better. So what's on the next slide? Okay, so this is my metaphor for how Unix as an infrastructure works, how it evolves over time. It's really, new requirements come in, and we started at the machine level, so we started out with just our PDP-11, and we wrote some assembly code, and then we maybe developed a higher level language like C, and we're building stuff up, and later we added the dynamic linking and the debugging and so on. So we're building stuff up, and we're trying to make it as uniform as possible in a kind of opportunistic way. That's how you avoid losing at Tetris, is try and create uniformity. So that's what's happening in the Unix world. Of course, in Smalltalk, it's all very, I meant to say that this is back to our comparison from earlier. And you see that, well, we said that we had to program from the outside and change things from the outside, but we know that we've got a little bit of infrastructure for doing it a bit differently. We've got a little bit of dynamic infrastructure in our Unix now. So in the Smalltalk world, it all happened very differently. So Smalltalk was a vision. It came down from on high, and a select few people were party to this vision. I assume that's sort of Alan Kay and maybe Dan Ingalls or someone like that. So very much sort of came down from above in this sort of fully formed way. You could also say that it's a bit of a cathedral. Eric Raymond would say Smalltalk is a cathedral, whereas Unix is a bazaar. So it's very much sort of it's a whole system, and it's not evolved through this Tetris-like process. But nevertheless, in the 80s, some things did happen with Smalltalk. And one of them was that we started implementing it in a way that was closer to the machine. So this is a paper from Peter Deutsch and Alan Schiffman about how to implement Smalltalk 80 efficiently. And they said, well, if the V code, so V code means the byte code, basically, so the interpreted code. If the V code in our Smalltalk system were translated to encode means native code. So if we compile this code, then we could eliminate the interpreter's overhead, and some optimizations would become possible. So this is basically the work that kicked off what we now know as just-in-time compilation and all the tricks which we could use to implement dynamic languages efficiently. So we can see that this sort of Smalltalk balloon is now it's moving a bit lower down. It's in reach of the stuff that's been building up from the bottom. And also remember that I mentioned we have lots of balloons. We don't just have Smalltalk. We have lots of dynamic languages. We have Python and Ruby and JavaScript, and they're all little balloons. And this was never really part of the plan, right? Because actually the very first implementations of Smalltalk were as microcode for the Xerox Alto. So the idea was that was just what your computer did. It just was a Smalltalk machine, and that was all you were going to need, right? I mean, Smalltalk's so great. So it's and maybe the world would have been nicer if that vision had taken off, but somehow we've ended up, for whatever reason, with a world where people want their dynamic languages and they want some other stuff on their machine as well. So this has sort of created a lot of problems in that it wasn't really designed for virtual machine style language implementations to interact with one another, to integrate with each other. So if I want to call some Ruby code from Smalltalk or some Python code from JavaScript or whatever, I mean, that's just off the radar, right? I mean, we can maybe talk to C if we're prepared to do some very nasty programming. But this was never part of the plan. So a lot of complexity has fallen out of the fact that it was never designed that multiple language implementations would talk to each other like this. So I'm going to zoom in a little bit on this problem of what we would now probably call foreign function interfacing. So this is how you get a virtual machine, like a Smalltalk virtual machine, to use talk to code that exists outside it. And I'm going to try and hopefully convince you, or at least get you thinking that it might be the case that FFI is not only evil, but also unnecessary. So to convince you that it's evil, here are some little bits of software engineering wisdom. We all know that these are good ideas. So if we look at a program, we're going to target an interface, not an implementation. And if we target an interface, that interface should be one that hides change-prone details, should not be subject to change all the time. That's why we have interfaces, to isolate us from change. And then when we're building stuff, we don't want to have to repeat ourselves unnecessarily, because that creates a lot of maintenance overhead. So unfortunately, the sort of standard practice in foreign function interfacing is committing all of these sins So for example, I got this code. You don't need to read this code. The whole point is that it's horrible and you shouldn't read it. But this code is actually from a tutorial in V8, so V8, Google's JavaScript engine. And this is saying, well, if you have a point data type with X and Y fields, and you've written it in C, let's say, and you want to use it from JavaScript, well, to get the field X, you're going to have to write some code like this. And then to get the field Y, set the field X, you're going to have to write some more code like this. This is insane. You know, why? I mean, it's just setting a field, getting a field. What's going on here? You know, but we've got used to this way of thinking that, you know, if it's foreign, then we're going to have to pay a high price to use it. But people do this all the time. Here's another thing. So we said interfaces should not be change prone. This is an email from the V8 project. It's saying, well, you know, one of the V8 developers says, well, we just changed this API that you're all using, but well, don't worry about it. You know, it's just a cleanup step, and it's not urgent. You know, it'll be okay. And this poor developer says, these changes break almost every single line of V8 using code I've written. And he goes on to rant about how he's going to quit using V8, and you know, who can blame him? So there's a third problem. So this is about the best you can do for FFI on a V8-based virtual machine at the moment. This is the Node FFI project. So we're sort of, it's wrapped up a lot of the complexity for us. So here we're trying to call some simple functions from the C maths library and the C library. So one of them is ceil from the maths library, and the other is A2I from the C library. You say, well, we've just got to tell the system that these functions exist and what their signatures are, and then we can get a variable that points to them, and then we can call them. So that's not too bad, but it's not very dynamic, is it? We've had to actually tell the system what we have before we can use it. So, I'm going to hopefully convince you that we can do better than that. Why can't we just do something like this? Why can't we just call the things? Why aren't they just there in the system? So I mentioned that Unix has a lot of dynamic stuff. So the question is, can we use the dynamic infrastructure that I mentioned, the debugging and dynamic loading infrastructure, to get the same effect, right? And it seems like we might be able to. So here's a little bit of C code that you could write that is basically going to dynamically retrieve, in the first snippet, it's going to dynamically retrieve a pointer to the ceil function for you just by giving its name, basically. So you say, well, we want a pointer to this ceil function. You see, it's basically got the same problem as the Node FFI stuff is, that we had to know what the signature is, right? We can't exploratorily discover these functions. We have to know, oh yeah, it's double to double. And we can also go the other way. So there's a slightly less well-known function called dladder that lets us say, okay, I've got this pointer. Tell me what's on the end of that pointer. So here we're saying, tell me what's on the end of this ceil pointer. It writes stuff into a structure for us. And then we can say, okay, yeah, it's told us it's called ceil. And that seems pretty useful, right? That's letting us dynamically explore what's in our process. It's better than what we could do with Node FFI. Unfortunately, this function only works for static objects, meaning objects that were existed at the program startup or when the library was loaded. So it's not going to include local variables, not going to include stuff we allocated on the heap. So it's kind of a start, but it's not solving the problem for us. So here's another quote from a 1980s paper, and this is about this is Tom Cargill's paper about the Pi debugger. And he really nails what the real difference is between Smalltalk and Unix here. It's not about static versus dynamic. He says, in Smalltalk's integrated environment, there's little distinction between the compiler, the interpreter, the browser, the debugger. They all cooperate through shared data structures. And there he means shared as in private to the implementation. They all have secret back channels between each other. And that's how they create the illusion of being integrated, magically integrated. Whereas Pi is this Unix-style debugger that he'd been building. And he says, well, it's an isolated tool in a toolkit environment, and that's the Unix way. And he says it integrates with graphics and external data and other processes through explicit interfaces. And he's not talking about FFI-style interfaces. I'll tell you what he is talking about in a second. But really, what I like to summarize this quotation as saying is that in Unix, programming tools are federated. Right? They're not one big blob of stuff that gets passed down from on high. They're built independently of one another. So you can have a compiler, you can have a debugger from a different vendor, doesn't know anything about your compiler. As long as they have some kind of explicit interface between them, then they can talk to one another. So I'm going to show you what that interface looks like. And I mentioned it's not really an API, it's more like metadata. So if we run the C compiler, and we tell it to generate debugging information, and I'm going to use my hello world program again. Is that going to work? Yeah, let's give that a try. Okay, and now we can actually see what information the compiler has left there for the debugger, so what that explicit interface is. So let's ask readelf to tell us that. Readelf, wi, hello. So you can see it's quite a lot of information. You don't need to read it all. But you can see that it's telling us there's a compilation unit here, and it's called hello.c. Fine, and it was produced by a particular compiler, the GNU C compiler, blah, blah, blah. You also say it tells us what the data types are in our program. So here it say we have a thing called long unsigned int, and that is 8 bytes of a particular encoding, unsigned encoding. And we have some more data types, and we should have a subprogram somewhere. Subprogram meaning a bit of code. So you say, well, we've got a bit of code, and it's called main. And it's even going to tell us some interesting things about main, like, well, it's got a return type, which is just a reference back to one of the data types that were given above. But it's also going to tell us that, well, it's got some arguments, and the arguments have a location. And here the location is saying, well, there's a place on the stack, which is the value of FB reg, it's not important, it's basically the base of the stack frame. And it's saying, well, it's 20 bytes away from that. And similarly, the next argument is going to be on the stack. It's going to say, okay, well, that's 32 bytes away from that. And it's got a bit more stuff as well. So you can see that it's actually a lot of information in there. It's describing to us the code that the compiler generated, but it's not prescriptive. It's not telling us what we need to do with that information. It's just saying, well, hey, this is what we've got. So that could be very useful in a dynamic context, right? We can discover what code we've got and what it can do dynamically. So again, back to our comparison, we see, well, we thought it was just opaque bytes, but actually we've got this detailed description of what those bytes mean, which could be pretty useful. So let me just take stock. We've got used to thinking about languages a certain way, which is that each language is a world. So maybe there's a Smalltalk world, and there's a C world, and there's a Python world, and a Ruby world, and so on. And so if we think about it that way, then of course it's going to be expensive to move between worlds, right? That's just space travel, doesn't come cheap. So maybe we can think about things another way. And the way I think we should be thinking about languages is as views onto a wider world. So language is like a lens that shows us what exists in our program. And that might be code in our program, data in our program, doesn't matter. But the point is that code and that data exists independently of the language. The language just gives us a way of looking at it and a way of expressing what we want to do with it. So this is a little bit of I'm going to tell you a little bit about a project that I've been working on. It's a little bit of a side project. It's not quite my bread and butter. But it's called liballocs, and it's supposed to be a Unix-style extension that's going to let us implement languages in the way I've just described. So there's a couple of parts to it. One is that if we want to compile code statically, the static way, then we're going to run a little wrapper around our compiler that's going to gather together this metadata and post-process it so that it runs, so that it's in a form that can be used fairly efficiently at runtime. So that's what this alloc cc thing is doing. It's really just going to run the underlying compiler after it's gathered a bit of information about that code. And then we've got a runtime library that's going to provide us some services that let us implement dynamic language features. And the LD preload thing just means load this library first because it really needs to hook in quite deep into the process. So what could we do? Well, we can give it a pointer, and it can tell us what's on the end of that pointer. That's what the first is doing. That's giving us some kind of type information about what's on the end of the pointer. So this is a lot like what the deal_adder function was doing for us, but that didn't really give us any type information. It just told us, well, there's a thing, it's got this name, it's got this size. So it's really just telling us that we've got some object, but not really any type information. So this is going to describe to us the type information, and It's going to work for objects on the stack or on the heap. It's not just limited to static objects like dladder was. And we've also got a few other calls to give us some more information, like what kind of memory it's in. Is it on stack or heap or static or something else? It can tell us things like where in the program it was allocated and so on. So in this talk, sadly, I could tell you all about how this works, but I'm just going to give you a little bit of a taste of what the challenges were in making this work. So suppose you're writing some code in C and you have an ellipse data type, then it's probably going to end up looking a bit like the thing at the top. And you see that objects are going to be nested inside each other. So you've got a point that's inside the bigger ellipse, the point representing the center. And we can take the address of any of these fields, or I can take the address anywhere in this object. And that's a big contrast with the way objects are in a typical virtual machine language implementation, where we make sure we only take the address of the beginning of an object, and then we have a header, so that makes it easy for us to get to a description of the object, and then we can say, okay, now we can do dynamic dispatch on this object, let's say. So we have to deal with the top case, and that involves keeping a lot of metadata in a separate structure, and then finding a way to index quickly into that structure from an arbitrary pointer. And there's another complication, which is that in big programs, the way that allocation happens is actually quite involved. So we end up getting memory from the operating system, but then that memory will sort of get parceled out gradually in a sort of hierarchy of allocators. We won't just have one central allocator. So we might have our sort of garbage collected heap on one hand, we might have the C libraries malloc on the other, we might have some other malloc, and then we might take some memory allocated from those in a big array and then parcel that out to some separate clients. So in a big program, we've got to understand at runtime what this structure looks like, so what the pattern of allocations is and what allocation a particular piece of memory belongs to. So again, we have to keep some clever index structures. We have to notice when allocations happen. We have to keep tracking this as the program runs. So I'm going to give you a very quick demo. This is so bleeding edge that if it doesn't crash, I'll be a very lucky man. But just to give you a little feel for what kind of thing I'm talking about. So again, I've been hacking V8. So I'm sorry that I would switch from JavaScript to Smalltalk to JavaScript. I'm sure I've offended some purists. But let me see if I can show something for you. It's not going to be earth-shattering, but this is a hacked version of Node, and it's hacked to use my liballocs infrastructure that I mentioned. So it's going to, instead of, well, I'll show you. Let's just get it running. So, okay, so in Node, you have this process object, and it can tell us things like the PID of my process, which is, even I can't read that, 8823. Anyway, it's printed out something. Oh, it looks better on the projector, actually. Okay, so anyway, so we have this process object. So remember that languages should be views, not worlds. So what I want is for this process object to show me all the code in my process. Doesn't matter whether it was JavaScript or not, right? So, so at the moment, so using my hacked liballocs, we can actually, for example, we can call printf. So this LM object stands for link map, and it really says just all the stuff that's linked into my process right now. So I can call a hello world function that was written in C. I didn't do any FFI wrapping or anything. It just knows. It can just see that it's there. And hopefully this will work. Does that look good? Does that look good? Yay. Okay, so that's, okay, it's not very impressive so far. But then we can also do stuff like we can load new code into our process. Oop, whoa, what was that? I hope that wasn't anything important. So we can load new code, and so say we want to load some library, something pretty boring, lib zip.iso.2, and then so we've loaded this library now. I was really hoping that, so it can tell us returned as an object. It hasn't yet shown you what's inside that object. There is actually stuff in the object that dlopen returns to you. So yeah, I was hacking away last night and ended up breaking everything horribly, but that will work very soon. So I mentioned it as a side project, didn't I? So now we've got this libzip in our process, so we should be able to, call some libzip functions, let's say. So what do we want to do? We can just see what there is. I don't know what there is. I've never used this API before, so it can tab complete for us, can it? Yay! Okay, so it can show us what's in the process, and then we can call these and do some fun things with zip files if we want to. So I'm going to stop the demo now just so that I have time for questions and finishing up and so on. But I'm happy to give you a longer demo later if you want to catch me. So we've done that. So Okay, so that's all well and good, but it seems like all I've done is basically made C available in JavaScript, which is, it's pretty handy, but it's not exactly the vision that we wanted. So to really complete this circle, what we want to do is have our JavaScript engine or our Smalltalk, whatever it is that we're working, actually expose back to the system what code it has created, so what code has been programmed in JavaScript or Smalltalk. And the way we need to do that is to generate the same metadata that we have from the C compiler. So if we can do that, which is, I mentioned that nowadays JavaScript or Smalltalk implementations are very much compilers internally, right? They're just doing similar stuff to what our C compiler was doing. So there's no barrier to generating that metadata from our JavaScript code too. So that's going to be my next sort of technical challenge to make this stuff work. And once we've exposed that back, that metadata, then we have this property that code is just stuff that is described, and it's the fact that it's written in a particular language just becomes an implementation detail of that code. It's not that code is trapped in a particular world. It's just that, well, we chose this language to express this particular code, but it's all just code that has metadata. So it's all stuff that we should be able to use from any context, from any language. There's a technical challenge remaining after we've done that bit, which is garbage collection. This is a picture of garbage collection. So the R means roots. So we start out with some roots, which might be our stack and our global variables. And then we follow pointers, and we end up in the heap, and we keep following pointers. And we do this C thing. C means collect. We figure out which ones are not reachable, and we throw them away. We're going to have to start unpacking our notion of what garbage collection is if we want to make this work seamlessly, because of course we've got lots of different ways in which our memory can now be managed. We might have some objects that are mallocked, some objects that are in this JavaScript heap, and we've got to make sure that reachability works across all these different areas. So we're going to have to start unpacking this idea into distinguishing between tracing, so tracing is following pointers and establishing reachability, and then freeing stuff, which is what we do when we found that it's not reachable anymore. And then there's moving stuff around, which a lot of garbage collectors will do to help avoid fragmentation and keep things organized efficiently. So once we've distinguished all these things, we might find that some parts of our program, some of the heap, we just trace through it because it's managed manually. Like say it's malloc, the malloc heap. We just trace through it so that we can find pointers into the other bits of the heap, other heaps. And then in some other region, maybe we know that we can free stuff in here. We want to free stuff here automatically because it's supposed to be garbage collected, but we're not going to move it around because maybe we've made some assumptions that these objects are not going to move. Maybe we want to use them from C code that doesn't know about objects moving. And then we might have some other heap that's much more like a normal heap where we can do everything. So we can trace, we can free stuff, and we can move stuff all at the same time. So that's another technical challenge that's on my horizon. I don't think it's insurmountable. So if you'd like to join me, I couldn't resist putting this picture in. So this stuff is on GitHub, and I encourage you to email me if you're interested, and you can try it out. It's a bit of a palaver to build, but I can definitely help you out with that. Also, something Darth Vader might not say is if you have any feedback or wish list items, then I'm very happy to. I'd just love to hear from you if you think this is a good thing. Right? If you'd like to use such a system, if you think that this is the right direction, it would be great to hear from you. And I think, I've got some image credit, lots of images, which many people more talented than I produced. So I thank them. And just a few conclusions. So Unix is more dynamic than people think, and languages should be views, not worlds. Let's build that infrastructure, and thanks for listening. I'm overwhelmed. Yes, please.
So if you're using JavaScript to link into C, and that assumes that you know what that printf thing was to begin with, someday in the future, I hope you can get your JavaScript to coerce the C to be more like a Smalltalk system. So you could say, what are you, what do you do, and how do I know you do that better than this other library?
Right, so the comment was, I'm supposed to repeat every comment, that at the moment it's just mapping C into JavaScript or Smalltalk or whatever, so it'd be nice if we could make that C look more like a Smalltalk and be more descriptive. So are you thinking about the class sort of the class system, the meta system of Smalltalk?
Well, you know, and part of me was thinking about Joe Armstrong and his talk, and you know,
Okay.
we've got this huge amount of stuff, and how do we reduce it? And you know, let's say there are 1 million printfs out there. Maybe one of them is really better than all the rest, and we should be able to discover that that printf is better. And then part of me was thinking about the next computer, and a friend of mine said, you know, I really wish Steve Jobs had not used Objective-C and just written the whole thing in Smalltalk, but he didn't. He made it more he made it kind of static dynamic a little bit, and now you look at where Apple's gone, and it's very locked down, and industry has the tendency to get very closed, and people I know have always wanted things to be open, and if we can address the security concerns, maybe we can open it up, but anyway, this is a lot to talk about.
I would love to talk to you later about any and all of that, so thanks. Yes?
So you talked about sort of doing the reverse direction as future work, sort of exposing the stuff that Node produces for the JavaScript using some kind of interface. Have you thought about what that interface would be? Because it seems like so far it's been pretty focused on the kinds of artifacts that the C compiler produces, and I guess what I'm getting at is, you know, there's a lot more in these different languages than, you know, just the fact that, I mean, the things that they produce are actually going to have sort of fundamentally different representations, and how are you going to sort of reconcile them?
Yeah, so I've thought about this quite a lot. The short answer is that, to repeat a theme of the talk, they're not as different as you think. So, for example, maybe I should give you the full story offline, but basically, at the moment, when you're the JIT compiler in V8, let's say, and you generate some code, then you just put that code in a buffer that you're allocated, right? It would not be too much work to, instead of making that an allocated buffer, to make it a memory mapped file that has exactly the same descriptive structures as what the C compiler's output did. And then suddenly it's like playing Tetris again, right? You've got uniformity, and so hopefully things will work out quite simply.
But what if you wanted to do that for the code that the JavaScript code that does not have JIT?
So then what you can do is, so for uniformity, when you define a function, you basically want to generate a tiny stub that just calls into the interpreter, and that's super cheap, and you can put it in the same region, and so yeah, you end up with the fact that it calls the interpreter is internal to that stub, so yeah. Yes?
The problem when you expose C programs based on the C tags is that the C tags don't capture essential information such as ownership of the pointers. And you can run all over the information of metadata, that's not part of it.
Are you talking about memory safety?
I'm talking about who owns the pointer and who can modify this region or cannot, or this is not captured in the C tag, and therefore if you
Well,
just based on the point that has been formalized, you can easily corrupt your heap.
Right, I forgot to repeat the last question. Let me repeat this one. So the question is, because metadata that comes from the C compiler doesn't describe ownership of pointers and objects, then there's a risk of corrupting the heap and so on. So there's multiple issues here, but I'm not making C memory safe. None of these FFI systems do. So in that sense, this is a problem we're stuck with. Actually, I have some other work that is making C memory safe, so I can talk to you about that. And there is a lot of existing research doing that as well, by the way. I'm just doing it better. So that's one issue. Another is that, in general, you have there's always a case for putting more stuff into your meta model, if you like. So there's always something that in a given language, your data types don't express, but you want to have that information anyway. So actually, that's a very good argument for doing exactly what I've been showing you, which is that the metadata is somehow in a language neutral form that we can extend. So if I wanted to manually maybe write down some ownership constraints about pointers and a particular bit of code, I should be able to push that into my metadata, even though the compiler couldn't generate it for me because the language doesn't know about it. I could still imagine sort of linking in or patching up my metadata to include that information later, and then it all becomes available to the rest of the system. So yeah, it's definitely, there are some challenges there, but I don't see that. I think it actually fits quite well. Do we have time for one more question? Yes. So your question is, how does it compare to COM, Core, IDL? So the thing about those systems is that they require a lot of buy-in. Right? You have to choose the technology up front, and then you write your interfaces using their IDL, you run their compiler. But this is very much sort of opportunistic. We're just using absolutely stock tools. Okay, we've changed the VM, but that's all sort of, the user doesn't need to care about that. So we use our stock C compiler, maybe with a bit of a wrapper around it, but it's basically the same experience. And so you can get a lot more integration, a lot more opportunities for doing stuff that way if you don't have to sort of buy into some technology ahead of time. Maybe we're out of time because it's now 40 minutes after 10. Oh, one more. Okay. Hey.
So in your example, you were using like DL open to like pull in like shared objects. Have you thought about extending this to processes that are already running, kind of like your first debugger example? So you almost have like IPC sort of mechanism to query another world for like a view.
Right. Have I thought about a sort of distributed case where we're trying to get a handle on other processes rather than just a library that we've opened ourselves? Yes, I've thought a bit about it. I would love to think more about it with someone else, but yes, definitely it's on the table. It's just so much stuff to do. So yeah, thanks. Okay, thank you all for listening.